Magnetic flux through the area enclosed by a 300 turn 7.2 millihenry coil when the current in the coil is 10 milliampere. Options are given. When we pass current through a coil, flux associated with that changes. Hence, a back EMF is induced in the coil. We can relate magnetic flux and current by the equation Li equal to N into phi, since there are N number of turns. From this, we can find out magnetic flux phi equal to L into I divided by N, where L is the self-inductance. Self-inductance is given 7.2 millihenry, that is 7.2 into 10 raised to minus 3. I is given 10 milliampere, that is 10 into 10 raised to minus 3 ampere divided by N is 300 turns. When we calculate this, we will get 240 nano Tesla meter square. So option B is the correct one. Faraday's laws are consequences of conservation of. Options are given. We know that by Faraday's law, EMF induced in a coil, we can write it as minus d phi by dt, where phi is the flux, magnetic flux. That is, when the magnetic flux linked with the coil changes, an EMF is induced in that. Here, how we can change the magnetic flux? Either by moving this coil or by moving a magnet beside the coil. So, here mechanical energy is converted into electrical energy. That means this is in accordance with the law of conservation of energy. So option A is the correct one. A 50-turn circular coil has a radius of 3 centimeter. It is kept in a magnetic field acting normal to the area of the coil. The magnetic field be increased from zero point 0.1 to 0.35 Tesla in 2 milliseconds. The average induced EMF in the coil is. Equation for EMF is E equal to minus d phi by dt. If there are n number of turns, then minus n into d phi by dt, or we can write minus n into delta phi by delta t. We also know that phi equal to B into A, where B is the magnetic field and A is the perpendicular area. Or we can write delta phi equal to B2 minus B1 into A. Let us substitute this one, that is minus n into B2 minus B1 into A divided by delta t. Just substitute the values. N is 50, B2 minus B1, that is 0.35 minus 0.1 into area. Area is, it is a circular coil, so it is pi into r square. R is given 3 centimeters, that is 3 into 10 raised to minus 3 meters whole square, divided by time 2 millisecond, that is 2 into 10 raised to minus 3. So when you calculate the value, you will get it is 17.7 volt. So option B is the correct one. The magnetic flux linked with the coil at any instant t is given by phi equal to phi t cube minus 100t plus 300. The EMF induced in the coil at t equal to 2 seconds is. Equation for EMF is E equal to minus d phi by dt. That is minus d by dt of phi is given phi t cube minus 100t plus 300. We already know that d by dx of x raised to n is n x raised to n minus 1. Let us use this general formula, that is minus first d by dt of first term phi t cube, that is 5 into, Here n is 3, so it is 3 t raised to n minus 1. 3 minus 1 is 2 minus 100 into dt by dt, that is 1. So it is minus of 15 t square minus 100. Let us substitute the value of t, 2 second, minus 15 into 2 square minus 100. That is minus of 15 into 4, 60 minus 100. So when you calculate this, you will get 40 volt. So correct option is option B. Two similar circular coaxial loops carry equal currents in the same direction. If the loops be brought nearer, the currents in the loops. Options are given. In the question, two loops are given and the current is flowing in the same direction. As the loops are brought closer, the magnetic flux linked with them increases. Magnetic flux increases, but an EMF is induced in each loop which opposes the change in flux, which opposes the flux that was there. So the current in the loop decreases. So the first option A is the correct one.